All right, let's consider a general situation. Let's supposing my source over here, my voltage source, is Vs angle phi 2. All right, we've got an impedance over here, Zt, and the current going into that impedance is It, and the angle is phi 1. Let's look at a couple of situations, a couple of possible situations. So let's look at a case where we've got Vs now leading the current It. We can say that the power factor angle, so it's the power factor angle, is really equal to what? Well, it's the angle between what the voltage and the current, so it's really equal to phi 2. And of course, when you take the complex conjugate of the current here, basically what happens, that angle changes, it becomes a plus, and so it's really plus what? Phi 1. And in this case, because the voltage leads the current, we can say that the circuit is really inductive. All right, another possible case. So in this case, we've got It actually leading the voltage, so we can say that the power factor angle is really equal to the phi 2. And of course, when you take the complex conjugate of that current, the sign of the angle changes, it becomes a minus, does it not? And so this is really a minus phi 1. And that means that we're talking about really an angle difference between It and Vs. All right? In this particular case, we can say that the circuit here is really capacitive. The current is leading the voltage. All right, let's take another example. Okay, in this case, we've got a current generator here. Value is 50 milliamps and the angle here is 0. We're going to assume RMS values again. We have this impedance here of the capacitor, which is a minus J318. The impedance of the inductor is J1.256K, and the impedance of the resistor is 0.5K. All right, what we want to do is we want to find the same things. We want to find the apparent power, we want to find the real power, we want to find the reactive power in this given circuit. Okay, so to do that, if we knew this current here, which we do, and we knew this voltage, well, then it's very easy. The apparent power then would be simply the voltage multiplied by the current, or really the complex conjugate of that current. Okay, so we need to first really calculate what? We need to calculate the impedance. That's the impedance looking in here, all right? So if I look in here, what is the impedance that this source over here is actually seeing? So we can say then that that is Zt, and that is going to be equal to, well, have we not got something in parallel here? We've got this impedance here, which is in parallel with the series combination of these two. So we can say that we've got, I'll write this guy in polar form. So this is what? 318 at an angle of minus 90. And that's going to be multiplied by the series combination here, so I'll write that down as what? 0.5K plus the J, 1.256K. All right, so that needs now to be divided by the sum of this plus this. So do that, and we'll say that we've got 0.5K plus the J, 1.256K, and then plus this bit over here, which is the minus J318. All right, so now what we need to do is we need to just evaluate this over here. So look, let's take this in really a couple of steps. And look, I really would like you to do this, just to check my work here, but do this. It will be good actual practice for you. So in the numerator here, we'll leave this 318 at an angle of minus 90. And then we're going to convert, since we've got multiplication here, we're going to convert this guy here, what? Yeah, to its polar form. And I'm going to say that that polar form is equal to 1352 at an angle of 68.29. And again, please check that, okay? That's divided by, well, if I look at this, I'm going to convert this over here. It's got the real bit, an imaginary part. I'm going to convert that to polar as well. So you want me to take that in really 2 steps? Yeah, I can, okay. So let me leave it in rectangular. I'll take it in 2 steps. That's 0.5K, isn't it? Dealing with these 2 parts here, I've got 1.256K minus 318K with a J in front. And so that's really what? A plus J 938. Now, the last step here is I need to convert this guy, what? Into, yes, polar form. So let's put an equals here. We've got the 318 angle minus 90, and that's multiplied by this 1352, and my angle here, of course, is that 68.29, and I'm now dividing by converting this into polar. We have 1063 and an angle of 61.94. Okay, now it's easy. Okay, I can multiply these 2 parts here, the magnitude parts, and then I can divide it by the 1063. And then I can add the angles, bring this angle up to the numerator, and changing its sign. So if we do all of that, we get that ZT is equal to 404.45, and the angle is a minus 83.65. All right, let's redraw the circuit. So what we have is our source over here, which is our 50 milliamps, angle 0. Okay, and now we've evaluated this ZT, so we can represent it really in this fashion. So here it is, ZT. And what we're now trying to find is really this voltage, V1. Remember, this is a current source, okay? So what we can say is that this V1 is really equal to that current, which is 50 milliamps, angle 0. And that's going to be what? It's going to be multiplied by that ZT, isn't it? So multiplied by ZT. So therefore V1 is equal to this 50 milliamps, angle 0, multiplied by ZT, which is this 404.45, angle minus 83.65. All right. So if we work that out, we have this voltage V1 then being equal to 20.2, and my angle is a minus 83.65. I'm in a position really to work out now what the apparent power is. So we can say S is equal to, what is it? It's going to be the complex conjugate of this current. Well, the angle 0 in this case. So really it's just the same, isn't it? It's just going to be this 50 milliamps. And that's multiplied by this voltage V1, which is of course this 20.2 at an angle of minus 83.65. So therefore my apparent power, S, is really equal to, multiplying these 2 out, this is really 1.011, units being what? Volt amps. And the angle over here is a minus 83.65. So let's now draw the power triangle. And then we can actually figure out what the real power is and what the reactive power is. All right, so here we go. What I've found so far is the apparent power, S. And we know this angle here is a minus 83.65. Okay? this component here, of course, is the reactive component, and this component here is, of course, the real power, P. So as before, we can say that that real power, P, is equal to S times the cosine of this angle, which is a minus 83.65. And if we work this out, that is equal to 0.1118 watts. The reactive component Q is equal to, once again, S times the sine of that angle, minus 83.65. And if we work that out, that comes out to a minus 1.005. Again, the units here being volts, amps, reactive. This minus sign over here indicates that really the load here is a capacitive load. Now, why don't you go back to the original circuit, taking the information that we have so far. You may have to do a little bit more work here, but why don't you see if you can work out all the components. That is, you already know what the true power, real power is, but could you work out the power, reactive power in the inductor, and work out the reactive power in the capacitor, and form a more complex power triangle and verify what we have over here? Okay, see you next time.